Right. Twitch.tv. Fantastic. Where are we? Right. Apologies for being so slow to start up. That is entirely my bad. I'm just going to set up for a moment. Yeah, as if that could be your fault. Right, where am I? Channel. Here we are. I can see now. I have sight. Good shit. Luckily, I do this all on stream so that you can see my idiocy every time. I'm not going to not comment on that. I'll do it every time. Yeah, you think by now I'd understand where in the world pop-out chat is. There we are. The answer is and will remain no. I will never not be a fool. Okay. Things are getting clean. The other day I broke my entire system by updating. I decided to get the extra section into testing, but not the greatest idea, to be clear. Because they'd update it in NVIDIA without updating the kernel itself. Broke the entire thing. Had to jump in with an Endeavor OS, what is it called? USB. USB worked, it did. Still though, this is Arch. Probably should have used an Arch ISO. Just hiding my face, to be clear. This will take a moment. Also, there's nobody here but me. Perhaps. I don't actually know about that. It's alright not to see anybody, though. Maybe I'll just do it by myself. I got no issue with that. I'm enjoying learning. We are here. It looks like it saved our position. Thank the Lord. I have no idea how to figure it out. Idiot, and don't actually read things. Like every time I completely... Oh, hey! Keith, you're here! Fantastic to see! Alright, let's see if I have my webcam on. Hey! Happy to see you, Keith. At least we'll have one of you here. There are 3 people watching. I believe 1 to 2 may be me. I don't know how Twitch works. Okay. How you been, though, Keith? You had a good week? Just checking to see if my audio is currently working. This is a collection of words intended to get my... there we go. Okay, hopefully there isn't an echo. There is a noise back. You sold your car? Got a newer one? That's good. Oh, yeah, stressful as hell. I hate that shit. Selling a car is one of the worst things, and getting a new one, horrible decision. What kind of car did you get? You get a decent one? Something that's gonna last you a while, or just whatever you could? Chevy Sonic? I know nothing about cars. I'm an idiot. I was just pretending to know. But I've heard good things about Chevy. Pretty good week. Nothing to talk about, though. It's literally just the rest of the weeks. Exact same system. I'm glad to hear you had a decent week, though. Right. Hopefully watching Dune. Did that come out? The new Dune's out. I really want to watch that. Currently reading The Children of Dune. No, I'm not. Where's the book I'm reading? I'm currently reading Dune Messiah. Fantastic book. Well, pretty good book. Not as good as the first. Got this next. But I love the series. Glad to get another series of it. It was a good, You're in God Emperor? Holy shit, you're way further along than I am, man. I've heard strange things about God Emperor. Apparently, a lot of people find it just went off a cliff. Very different. Messiah is nice. It's where he becomes a villain. Wasn't he a villain in Dune? I mean, he made drums out of the skins of his enemy. Not a good guy. But a certain Hubert's going after the entire. Oh, it gets worse. I'm very excited for that. That's going to be great. I love the forward. Hear that he just exits out of the entire book series eventually. Which is a strange thing, but I quite like the idea, concept. Yes, a moment. Oh yeah, his son turns into a worm. I've heard of that. I'm fairly certain that's true. That's an interesting thing. Right, there are 5 people watching. Hello, everybody. I'm very happy to see you all. 5 separate people? No, only one chatting. Is that 5 different Keiths? Is Keith here 5 times? Have you cloned yourself, Keith? Very excited to see that. Right, I believe that we are ready to go, though. 2 of them dropped off. No, just one. Just one clone? Okay, that's great. 2 of you, then. I'm just going to start reading, however. I think that we can start. Fixing an unsafe program, aliasing, and mutating a data structure. Just going to start, just go right through it. Unless there's anybody who wants to talk out, say anything different. But I'm just going to start. We are going to start with fixing an unsafe program, aliasing and mutating a data structure. Previously, we had gone through some other ways to fix an unsafe program. We are going to continue with this structure. Another unsafe operation is using a reference to a heap data that gets deallocated by another alias. For example, here's a function that gets a reference to the largest string in a vector, and then uses it while mutating the vector. We have a function, add big strings, putting in DST, which is a mutable vector, or a reference to a mutable vector, and source, which is a reference to an array of strings. We first start out letting a largest, which is a type of reference string. We get dist, which has read, and not write. Dist has read and write, but in this position, dist loses write. I don't understand why. Why does dist lose write? Oh, iter. Creating an iterator? We haven't discussed iter. I guess we'll discuss that later. Dist.iter max by what? Max by keys. I have no idea what that means. S, which is only readable. Dot length, and then unwrap. Right, so we're creating an interval and then unwrapping it. I, to be honest, have no idea what this line does. That's okay though, I assume they're going to explain. Ah yeah, we see down here, this example uses iterators and closures to succinctly find a reference to the largest string. We'll discuss those features in later chapters. But for now, we'll provide an intuitive sense for how those features work here. This program is rejected by the borrow checker because let largest equal ... removes the write privilege on DST dot. However, DST.push, which is later on in the for loop. Where were we? Requires the write permission. Again, we should ask why is this program unsafe? Because DST.push could deallocate the contents of DST, invalidating the reference largest. To fix the program, key insight is that we need to shorten the lifetime of largest. Do not overlap with DST.push. One possibility is to clone largest, creating a new copy of this, passing by reference, or a value. Well, that's not really true. It just creates the value in a new memory location, I believe. Here is a showing of that. Add underscore big strings. DST is a mutable vector. Source is just a reference to an array of strings. Let largest of type string equal dst.iter.max by keys s of length and wrap close. So that gets us the largest string in the vector. Sure. And for s in source, we check if the length is larger than largest.length. If so, we push to DSD the clone. Yeah? Destination, that's what DST means. Destination. Thank you for the explanation. So, in the destination string, we take from this from this array, the largest string, and push it in by cloning it from source. We do not mutate. We do not mutate source. Why is that okay? Oh, whatever. However, this may cause a performance hit for allocating and copying the string data. Another possibility is perform all this length comparisons first, and then mutate DST afterward. Let largest, we start out by getting the largest, how we normally have. We create a new variable called toAdd, which is a vector string, with .clone.collect. Source.iter.filter, which seems to be... We don't know what any of this is. We just have to move forward, I guess. I hate this. This is not how I tend to learn things. We have to just ignore that, I guess. However, this also causes a performance hit for allocating the vector toAdd. A final possibility is to copy out the length of largest. Since we don't actually need the content of largest, just its length. This solution is arguably the most idiomatic and the most performant. Function, add big strings. We take in the destination and the source, letting the largest length equal the use of type usize equal, well, yeah, so we just get it normally how we have been the entire time and simply pass back the length. Then, for each string within source, if it is larger, we simply push. These solutions all share in common the key idea. Shortening the lifetime of borrows on DST do not overlap with the mutation of DST. Fixing an unsafe program. Copying versus moving out of a collection. A common confusion for Rust learners happens when copying data out of a collection, like a vector. For example, here is a safe program that copies a number out of a vector. We simply have a vector of 0, 1, and 2, I32s. Let n reference equal a reference to a I32. Then we have reference v0, the first iteration. Let n of type I32 equal dereferenced n underscore ref. The difference operation. Where is the difference operation? Whatever. A dereference. Sorry, I am quite tired. The dereference operation, dereference n underscore ref, expects just the read permission, which the path dereference n underscore ref has. But what happens if we change the type of elements in the vector from I32 to string? And it turns out we no longer have the necessary permissions. Okay. Yeah, if the vector is simply a string, and we get the first reference, we cannot dereference. Okay. The first program will compile, but the second will not compile. Rust gives the following error message. Cannot move out of dereference s underscore ref. Is Rust saying that in order to be safe, we should always make a copy of our data and then work on that? Not necessarily, but that is a good idea. If we are, you do not want to mutate by default. If you are simply creating one variable to be mutated in one specific section, then no, that's unneeded. However, if you're passing into functions, that is normally a very good idea. Of course, there are other ways to do this. Of course, there are other situations where other methods will make more sense, but no. No, I really don't think it's always. But a lot of the time, yes. Making a copy of your data, working on that, and then passing the copy back is a good idea. And is the most idiomatic and safe, is the most idiomatic, safe way of writing code. So I guess kinda, yeah, you are right. Right, so the error is, cannot move out of a reference s underscore ref, which is behind a shared reference. Let s equals s underscore ref. Move occurs because the reference s underscore ref has type string, which does not implement the copy trait. We've seen that error before. The issue is that the vector v owns the string hello world. When we dereference s underscore ref, that tries to take ownership of the string from the vector. But references are non-owning pointers. We can't take ownership through a reference. Therefore, Rust complains that we cannot move out of a shared reference. But why is this unsafe? We can illustrate the problem by simulating the rejected program. Alright, so we got the vector, which is a string, hello world. Create s reference, we get a reference to the h in hello, the first position in hello world. Let s of type string equal the dereference to s underscore reference. These drops are normally implicit, but we've added them for clarity. Then we drop s and we drop v. V is the first vector. Right, so originally we have v, which points to, apologies, one moment, I'm going to have to fix that. I don't know if you can even hear it, but I can. I'll be back in just a moment. Hello, can you guys hear me? I think I'm back. Just going to check and see if you can hear me. Fantastic. If there's any issue with my audio, please feel free to tell me. And thank you for making it here, Keith. Looks like you're the only one chatting, but glad to see. Right, so in the first location, we have main, which has v, which is a reference to a pointer to hello world. S underscore reference is a reference to the same thing. A point in the heap, which points to the string hello world. And we have s in location 1, which is once more simply, s is a reference to hello world. In no way does it share commonality with s underscore ref or v other than, it skips the reference to the heap memory where we have a reference to heap memory for hello world, the array hello world. Location 2, we have v and sref, which point to the heap, which is moved. Location 2, yes, we drop s. We drop s, which is the reference to hello world. If we drop that, that means hello world is deleted out of memory. It is removed out of memory, is freed, or dropped, in this case, is what it's calling it. Meaning v and s underscore ref, they'll point directly to unused memory. This is so secondarily, we have s underscore ref in location 3, where we try and drop v, the original vector. Trying to drop it is a free after free, a freeing freed memory. That's a very bad thing, and you shouldn't do it, because that memory could be owned by another piece of memory. Not a good thing to do. So, pointer used after its pointee is freed. Use after free error. Can't drop that. Okay, so the drops are implicit, and this is why it's quite confusing, I guess. This is something that's easily confusing. it will drop it in opposite order of their creation. It tries to drop S, which it can correctly do. That's fine. But then it tries to drop V, which was created long beforehand. V is pointing to unused memory. So this is why we are not allowed to create a new string as a dereference of the original string. Makes sense. At least it does to me. I could understand completely if somebody didn't understand that. That is quite confusing. I do wish that these were a bit more implicit, or that it forced you to put them there or something like that, but I'm okay with that. What happens here is a double free. That's the error. Double free, that's what it's called. After executing let s equal, because a s string is not initialized. Oh no, s is initialized. S is initialized here. Initialization is simply saying, I'm sorry, I don't really understand what you mean here. But it is being assigned s underscore ref. S is initialized. It is initialized here. That is fine. But here is where the error lies. If we allow it to be assigned s underscore ref, we will eventually drop s, which is what s underscore ref is referencing. So we have, I don't know how to explain this a little bit better. Right, so s does not equal, this is really poorly done, I will say. This is, you can't really see this, can you? If we try and assign s to s underscore ref, we are not in fact pointing it to. Okay, that's not helpful at all. Right, so this, to be clear, is in fact the pointer to hello world. This is how you get to hello world as a string reference. And this references hello world, which is what v and s underscore ref are referencing. This is, well, not really, actually. Sorry. S underscore ref is the first one. That's not actually correct. But if we try and get s to equal the h in hello world, we, instead of pointing it to this, to the pointer to hello world, we point it to the h right here. So if we then drop s, we take s, which is the h, and drop it, this no longer exists. As you can see here, all the memory is gone. So if we try and drop it again, which is what implicitly happens, it breaks. Because we're trying to drop something that's already been dropped. Sorry, the issue is not the string not being initialized or it being assigned to sref before being initialized, but it is the fact that later on, s will get dropped, which will drop the h in hello world, that is free memory now, and then later v will get dropped, which attempts to drop h again. Does that make sense? I'll admit that was a bit rambly. Okay. I'm going to reread this for a moment, but we will continue. What happens here is a double free. After executing let s equals the reference s underscore ref, both v and s think they own. We don't have to get it all in the first pass anyway. You're correct, actually. Yeah. I hope this really drills this into our head. Really pounds it in, because I'll forget about it just continually. I will not remember this myself. Right, so both v and s think they own hello world. Your s is dropped, hello world is deallocated. Then v is dropped, and undefined behavior happens when the string is freed a second time. Oh, I was semi-wrong. The vector is... I can see why this is a bit confusing. So this is a list object that only has one value in it. It can be hello world and hello Bob, but they don't do that because it would make more sense to do that, honestly. I don't know. Yeah, that tries to deref or drop hello world twice. After s is dropped, hello world is deallocated. It is gone, it's deleted. Then v is dropped, and undefined behavior happens when the string is freed for a second time. Double free is a bad thing. After executing s equals dereference s underscore ref, we don't even have to use v or s to cause undefined behavior through the double free. As soon as we move the string out of s underscore ref, undefined behavior will happen once the elements are dropped at the end of the function. We will free both at the end. However, this undefined behavior does not happen when the vector contains i32 elements. The difference is that copying a string copies a pointer to heap data. Copying an i32 does not. In technical terms, Russ says that the type i32 implements the copy trait, while string does not implement copy. We'll discuss the traits later in this chapter. So to clarify, when we make s string equal the dereference to s underscore ref, it is pointing directly to where in memory we have hello world, pointing to this section of memory. However, if this was a bunch of numbers, as we see here, this would simply pass back the number 0, and we would have 2 points in memory where we had the number 0, because it can just copy 0. It can just have 2 sections of 0. It's not pointing back to 0. In memory, it's simply creating a new number 0. Over here is pointing to the one singular hello world. I can see why they do it, but I don't love it. That is quite confusing. Difference is that yep, we read that. In sum, if a value does not own data, then it can be copied without a move. For example, an i32 does not own heap data, so it can be copied without a move. A string does own heap data, so it cannot be copied without a move. A reference string does not own heap data, so it can be copied without a move. Because a reference string is simply a pointer, and a string, well, is also a pointer, but this is simply one singular reference to a singular piece of stack memory. Stack is over here, to be clear. So we can copy this over. We can make v equal s underscore ref, because these are both owned in the stack. They are simply pointers to the first reference, which is in heap data, which is a reference to hello world. That's fine. The string itself points to a bunch of heap data. Is a piece of heap data. Okay, so we are allowed to copy without moving anything within the stack. We are not allowed to copy without moving anything in the heap. Makes sense. One exception to this rule is mutable references. For example, a reference to a mutable i32 is not copyable type. So, if you do something like this, let mutable n equal 0, let a equals a mutable reference to n, let b equal a, then a cannot be used after being assigned to b. That prevents two mutable references to the same data from being used at the same time. Okay, so to clarify, a equals 0, a equals this n, a is n, they are the same thing, and b is n, they're the same thing. So if we change a, that changes b and n. That's not something we want. So we can only have one thing which can be changed, which can change n at the same time. May that be a or b. And when b dies, it will go back to a lot of the time. Sometimes not. Sometimes both will die. In the end, n is what will regain all privileges before dying itself. I believe. That's my understanding. Could be wrong, however. So if we have a vector of non-copy types, and Rust checks for these links, compile and throws an error. Absolutely. And that is a very good thing. This is what the borrow checker is. It just ensures that you're not using it in a way that could cause memory errors in the future. In C, in C++, in a lot of other languages, it can cause these errors. You can find yourself changing things in different orders. You can have 4, 10, 30 different references to the same thing, which can change a piece of memory at any point inside the program. This can cause a lot of issues, a lot of errors, and you got to track it down because you don't know what's changing the thing that you need to be unchanged. Rust ensures that you do things in a safe manner, and it does that before it even runs. I like that a lot. That is a very good thing. Alright, to continue on. So, if we have a vector, non-copy types like string, then how do we safely get access to an element of the vector? Here's a few different ways to safely do so. First, you can avoid taking ownership of the string and just use an immutable reference. Okay. This is just like if we want to read it out, like with a print line, as we see here. Let v equal a vector of strings as a vector. This is hello world. So we have a list of one item, and that one item, hello world. And we have as reference, which is a reference to a string, and it equals the first member of v. Sorry, a reference to the first member of v, which is hello world. They could have done so much better. I wish they had done so much better. This can be confusing. I don't understand why they didn't create a vector with more than one element. Second, you can clone the data if you want to get ownership of the string. Alright, so to confirm here, we are taking a reference to hello world that cannot be altered. We can't change it in any way, shape, and or form, but we can read it, which is fine. And we can pass that around perfectly fine. This is useful if we just want to print some stuff out, want to add something to a database, want to get a user choice and then change behavior based on said user choice, or perhaps take in configurations from a file. These are quite useful things these would be what that would be used for. Those are some examples. Second, you can clone the data if you want to get ownership of the string while leaving the vector alone. Okay. We have a vector that has hello world. We create a new immutable string from the first first string in the vector b, and then we clone it. So there are now two separate hello worlds. We then put in an exclamation mark and print it out. Okay. Finally, you can use a method like vec::remove. Remove the string out of the vector. Okay, why does remove pass back, return the removed string? I prefer the word pop. Get that in other languages, I guess. Alright, so we have a mutable vector called v, which is just holding a string called hello world. We then remove hello world from this vector, meaning we have an empty vector. The vector has nothing in it. And then we pass back hello world to s, which is in a new piece of memory. Then we add push, and we print it off. Confirm. There are two different sections of memory. We have hello world in one. We then delete it. We then pass it back so it exists for a moment in two different parts, and then delete it from one. In the end, we've taken hello world and moved it to another place. Essentially, that's... Well, I shouldn't be using the word move, because that is another thing in this language, but we have deleted it from one location and added it to another. Fixing a safe program, mutating different tuple fields. The above examples are cases where a program is unsafe. Rust may also reject safe programs. Okay? One common issue is that Rust tries to track permissions at a fine-grained level. However, Rust may conflate two different paths as the same path. Let's first look at an example of fine-grained permission tracking passes the borrow checker. This program shows how you can borrow one field, tuple, and write to a different field of the same tuple. Okay, we have a name, which is a tuple, which holds Ferris and Rustation. Name, name.0, and name.1 all have read, write, and ownership. Let first equal a reference to name.0. Now, name itself loses right and ownership over the entire thing. We have name.0, name.1, and we have name.0, and name.1. It loses all permission over all of those things. And first gains write, read, and ownership over first. The dereference does not own first, so we can't actually change Ferris. Name.push underscore string, comma, Esquire. That shouldn't work. Name.1. I guess we have ownership. Oh, okay, yeah, never mind. I'm entirely wrong. Name.0, because it's the first name, is no longer owned. Alright, sorry. I guess what it's trying to say here is that we have lost ownership and have lost write privileges over the word Ferris, but not Rustation. So, stop that. Why have you done this? So, alright, here we are back. Apologies for that. So, here, when we get the first name equaling a reference to name.0, which is Ferris, the string Ferris, and that is all it is. Name itself, and also name.0, the first element, Ferris, lose right and ownership. However, Rustation still keeps said ownership and write permissions, which is quite useful. I understand why name loses ownership, because if we're currently using first, and then we try and move name, we try and delete name, we try and change name in any way, it's gone. And if we try and use first after that, that would be a use after free error. However, since Rustation is not copied anywhere, it is not borrowed anywhere, it's perfectly fine to utilize. I can see that. So we can add comma, space, Esquire to the end of Rustation. This will print Ferris, Rustation, comma, Esquire. The statement let first equal reference name.0 borrows name.0. This borrow removes write and ownership permission from name.0. It also removes write and ownership permission from name. For example, one could not pass name to a function that takes as input a value of type string, colon, a comma, string. But name.1 still retains the W permission. So doing name.1.push underscore string is a valid operation. However, Rust can lose track of exactly what paths are borrowed. For example, let's say we refactor the expression reference name.0 into a function get underscore first. Notice how after calling get underscore first reference name, Rust now removes the write permission on name.1. Okay. At least they're being honest about a failure here. I mean, I don't see why that's wanted behavior. The name takes in a reference to a tuple with string and string, and outputs a reference to a string. This gets the first name. Let mute name equal, we've seen this before, first, lose name, store equals get underscore first, referencing the name, which loses the right and ownership over all three parts of name. Name itself, name.0, which is Ferris, and name.1, which is Rust Station. And if we try and push, we no longer have write permission. Failed. Alright. Now we can't change Rust Station, and Rust will return this error. Name.1 is mutable. Cannot borrow name.1 as mutable. It is because it is also borrowed as immutable. The immutable borrow occurs when we call this function and borrow the entirety of name. Immutable borrow occurs here. At name.1. Okay. And then we use it here. I can see. So what it's trying to tell us, I'm assuming, is that we can't utilize, if we utilize name and pass it into a function, then we lose ownership over all of its under all of the subpieces of the tuple. However, if we utilize a single part of the tuple, it will not. What if we simply passed in name.0? Would that fail? That's strange, since the program was safe before we edited, before we made an edit. The edit we made didn't meaningfully change the runtime behavior. So why does it matter that we put reference name into a function? The problem is that Rust doesn't look at the implementation of get_first when deciding what get_first reference name should borrow. Rust only looks at the type signature, which just says some string in the input gets borrowed. Rust conservatively decides then that both name.0 and name.1 get borrowed, and eliminates write and own permissions on both. Okay, that's perfectly reasonable. Because it doesn't understand that we're just using this. It's not actually looking at the code and deciding what's being borrowed later on. Simply looking here to see that we have two strings, and one string, a reference to a string, is being passed back, and thus we must borrow the entire thing. Makes sense. Remember, the key idea is that the program above is safe. It has no undefined behavior. Future version of Rust may be smart enough to let it compile, but for today, it gets rejected. Okay, so I was right, that's probably not intended behavior. So how should we work around the borrow checker today? One possibility is to inline the expression reference name.0 like in the inline original program. Another possibility is to defer borrow checking to runtime with cells, which we will discuss in future chapters. Okay, I'm glad that it said this to tell us that, hey, there are some issues with the borrow checker currently, and sometimes you get errors that shouldn't be an error due to the fact that you're not creating an unsafe program, but that is simply an issue with Rust today. I'm glad that it tells us that instead of pretending that Rust is perfect. Fixing a safe program, mutating different array elements. A similar kind of problem arises when we borrow elements of an array. For example, we observe what paths are borrowed when we take a mutable reference to an array. Create a mutable array, 0, 1, 2, 3. We create x, which is a reference, mutable reference, to A1. So that will be the second element. A, the array, loses read and write. Then, reference to x, so that would be 1 itself, we are changing the second element in the array, plus equals 1. That will equal 2 at this point. Print line, A, colon, question mark. Cannot remember what that does, to be entirely honest, and I don't really care. Rust borrow checker does not contain Rust borrow checker does not contain different paths for A0 and A1, and so on. It uses a single path A underscore that represents all indexes of A. Rust does this because it cannot always determine the value of an index. For example, imagine a more complex scenario like this. Let index equal a complex function. let x equal a mutable reference to a, and we are just putting in the index. The index could be anything, so at compile time, we can't really check on that. What is the value of index? Rust isn't going to guess, so it assumes index could be anything. For example, let's say we try to read from one array index, or writing to a different one. We have immutable a, which is 0, 1, 2, 3. We have a reference, mutable reference to the second element in the array, 1. Let y was a reference to a, 2, which is the third element in the array. And the dereference of x equaling this slot, plus equals the dereference of y, which is this slot. That would equal 3 in this scenario. However, we cannot that won't work, because where will this fail? Yeah. However, Rust will reject this program because a gave its read permissions to x. Yeah, that's, of course, why didn't I read? Apologies again, very tired. But here, we have given up read and write permissions to a. It will fail here, because y tries to read a, which no longer has read or write permissions. The compiler error message says the same thing. Cannot borrow a underscore as immutable, because it also borrows a mutable. Apologies once more, very tired. Cannot borrow a as immutable, because it also is also borrowed as mutable. Let x equal a mutable reference to a. Mutable borrow occurs here. Immutable borrow occurs at let y equal a reference to the third element in a. Mutable borrow is later used here. I think that's quite understandable. Again, this program is safe. In cases like these, Rust often provides a function in the standard library that can work around the borrow checker. It is safe, yeah, but due to the fact that we don't know if it's always going to be 1 or 2, it could become unsafe at a later point. In this current situation, it is safe, but the Rust checker cannot always check to ensure. I think that's quite understandable, actually. But in this specific situation, it's always going to be safe. Why can the Rust borrow checker not understand that? Alright, at the very least, we are going to use splits for working with arrays whenever we want mutation like this. Again, this program is safe. For most cases like these, Rust often provides a function in the standard library that can work around the borrow checker. For example, we can use slice, split at mut. Right. Mutable a equals 0, 1, 2, and 3. Let the tuple of a underscore l and a underscore r equal. Sorry, it's not a tuple. We are just defining two different. We are simply defining two different variables. A dot split at mut 2. So I'm assuming we are creating two different arrays here, starting at here. A left, that's horrible, equals 0 and 1, and a right equals 2 and 3. Let x equal a mutable reference to a left 1, equaling the second element in the array a underscore l. That points to this. Let y equal a reference to the first element of a right, equaling the first a. Then we simply add y, add the thing which y is pointing to, dereferencing y, getting 2, the value 2. And we are adding that the value in the location here, which will equal 3. You might wonder, But how is split at mute implemented? In some Rust libraries, especially core types like vec or slice, you will often find unsafe blocks. Unsafe blocks allow the use of raw pointers, which are not checked for safety by the borrow checker. For example, we could use an unsafe block to accomplish our task. Okay, that makes sense. Yeah, so the borrow checker can't work with it, so we have to tell the program, Rust, hey, I know what I'm doing. This will not cause an error. Please leave me alone. Good to hear. We create 0, 1, 2, and 3, creating a mutable reference to the first mutable as just typing it as a mutable dereference I32. Let y equal. Why do we have to define it like that? Then we simply do this within an unsafe block. Do not do this unless you know what you are doing. Sounds like why Rust is starting to be used in the Linux and Windows kernels. Yes, it's a very good thing to be used in these sections. What was it? 70% of all security exploits are memory errors, according to one study, which has some issues, but still fairly good. A lot of these can cause a lot of major issues. Like if we try and use after free, people can change the value of a memory that's used by a different program. Let's say the Windows kernel itself. And then either A, read after use, like if somebody tried to post out some code that could in fact be unused, you can just read stuff like passwords out of memory. Very dangerous. I would heavily suggest reading more about that if you want to convince yourself why Rust, or something like Rust, is a very good idea. It's also being used by NASA recently, and the government even stated that the government even stated that Rust should be what people move towards, and that newer programs created by government structures should be utilizing Rust. The government of America, by the way. I'm Canadian, so not my government, your guys's. But, well, I assume. I don't know where you live, Keith. Yeah, very good system. Unsafe code is sometimes necessary to work around the limitations of the borrow checker. As a general strategy, you live in Texas. Oh, I'm so sorry, my friend. I'm so sorry. Unless you like it, they got guns. Cow. I want to be a cowboy, baby. Let's not get into too much politics, though. As a general strategy, let's say the borrow checker rejects a program you think is actually safe. Then you should look for standard library functions like split at mute that contain unsafe blocks which solve your problem. We will discuss unsafe code in chapter 19, quite far from now. For now, just be aware that unsafe code is how Rust implements certain, otherwise impossible patterns. Okay. Don't use unsafe. If you're listening to this, if you're reading this, never use unsafe unless you know exactly what you're doing and why what you're doing is always safe. Otherwise, why are you using Rust? Very glad that it's safe by default. Which of the following best explains why an I32 can be copied without a move, but a string cannot? A string owns data on the heap, while I32 does not. I believe that to be correct. A string can be placed on the heap, while an I32 can only be placed on the stack. I don't believe that's true. An I32 is smaller in memory than a string? No. An I30, that depends, actually. A string can be smaller than an I32. But that's irrelevant. An I32 is a primitive type in Rust, while a string is not. That is incorrect. Both are primitives. I believe this to be the correct one. A string can be placed on the heap, while an I32 can only be placed on the stack is incorrect. You can place I32s on the stack. On the heap. First is correct. The following code snippet does not compile. Let s equals string from hello world. Let s underscore ref equal the reference to the string. Let s2 equal the dereference to the string underscore ref. Then we print s2. Which of the following best describes the behavior that could occur if this program were allowed to execute? Yeah, that's a double free. The read of s2 in print line is a use of freed memory. That is incorrect. At no point do we free s we don't free s or s underscore reference before this point. There's no undefined behavior in this program. There is. The string is freed twice at the end of the program invisibly. It happens. It happens, but it doesn't tell you. The dereference to dereference s underscore ref is a use of freed memory. That is incorrect. That is not correct. Alright. I believe this to be the correct answer. I hope everybody agrees. I think that's been well explained. Actually, no. I think it's completely understandable if you don't fully understand why. There are some issues in their explanation. The following program does not compile. Function, copy to previous, takes an immutable reference to a vector of type i32 called v. I is the size of the entire structure, I guess? Alright, no, I is simply the index, which is of type useSize. Let n equal immutable reference to v with I, of the index I. Reference n equals v I minus 1. And then we return the value, which is inside the location I minus 1. I think I hate how they don't put return here, because I don't think this returns anything. I don't know what n does. Why are we creating n? Doesn't matter, I guess. This is just for something else. This is just for explanation. It doesn't need to make sense. Let mutable v equal a vector of 1, 2, 3, copy to previous, pushing v in. And we are using the index 1 as I. Which of the following best describes the undefined behavior that could occur if this program were allowed to execute? First option, the read of v, I minus 1, is a use of read memory. This is incorrect. There's no undefined behavior in this program. I believe there is. The borrowed reference mute v, I, frees a pointer to freed memory. Is there a pointer to freed memory at some point here? It has to be. It keeps saying freed memory. Is there not an issue? No, we don't use anything afterwards. So we have, let's go through the flow here. I am receiving notifications. That's good to hear. Thank you. I should turn that off, because there will be some stuff that you guys should not see, if that is allowed. Sorry about that. I don't care that much. If you guys know it, I don't care. Oh no? Sorry, Keith. Yeah, actually, I am going to turn that off. Sorry, just a moment. I have to turn off something that shouldn't have really been on. Just gonna start giving you guys notifications of the things that I am doing. There we go. It shouldn't do that again. Right. There is an issue here. I believe so. Let's go through what happens. We create a vector 1, 2, 3 with a mutable v. We pass in a mutable reference to v. Ownership, write, and read permissions over v are lost. And it pushes in v. I see no issue here. V, that is correct. Let n equal a mutable reference to v 1, which is an i32. Oh, that's fine, because it's an i32. You can do that. No, you could have done that all along. And that is n. And then n is changed. N, which is a mutable reference to the number 2 within this vector, and has ownership, has write permission. Okay, yeah, I don't think there is any undefined behavior here, because n will have ownership, will have write permission, and will have read permission, and at no point is any of this stuff freed until at the end of main. And we aren't returning anything either. Yeah, we aren't returning anything from this function. This function returns nothing. I guess there is no undefined behavior here? There is, then it's quite confusing, and is something which I'm never going to catch. Right. Consider the function that is simplified Consider this function that is a simplified variant of a function from the previous quiz. As PhD to a person's name is just it takes in a name, which is a reference to takes in name, which is a reference to a string. Let mutable name equal the value, a reference to the string, a dereference of name. Name.pushString, comma, eh.d. Rust break. The Rust compiler rejects this function with the following error. Cannot move out of dereference name, which is behind a shared reference. Move occurs because dereference name has type string, which does not implement the copy trait. Oh, consider borrowing here with the reference to the dereference name. Assume that the compiler did not reject this function. Select each, if any, of the following programs that could possibly cause undefined behavior if executed. If none of these programs could cause undefined behavior, then check none of these programs. Alright, let's go through this. We have name equals string from Ferris. Let name underscore rev equals the reference to the name. Award PhD is the reference to the name. And we print name underscore ref. Right, so string has to be destroyed and then put into new memory because we are adding stuff to the string. That will create undefined behavior. If this is fine. If this was compiled. That will cause undefined behavior, I am fairly certain. Let name equals string from Ferris. We are passing in a reference to name, which is destroying, and then recreating Ferris with the colon, PhD, and then outputting name. I think that's fine because the name will still be a reference to the data. I believe so. Perhaps it won't be. Let name equal string from Ferris, and then just passing in the name. And not utilizing it. Well, oh no, name will be destroyed. Right, so that will cause an error because name will no longer be pointing to the data. Name.pushString, PhD, destroys it, creates a new thing with a new pointer to the thing. And name no longer points to... Yeah, okay, that's shadowing too. Name will point to it. But the original name will not point to it. That is wrong. However, we are perfectly allowed to have a pointer to something that no longer exists, as long as we don't use it. That's fine. I hope that was followable. I could understand if not. I should have went over that more. If I got it wrong, we'll go over it. Determine whether the program will pass the compiler. If it passes, write the expected output of the program if it were executed. Let mutable point equal an array holding 0 and 1. Let mutable x equal point 0, which will reference the first element 0. Let y equal a mutable reference to point 1. I don't think it will. Okay. Let x plus equal 1. Let y, that can't work. Oh yeah. Let the dereferencing of y plus equal 1. Print point 0 and point 1. This will not compile. I really don't think it will. We have point, and then we put in the first value inside of the array point to x, which is immutable. I believe at this point will lose read, write, and ownership, but at the very least ownership to x, even though this is a number itself, even though it is an array of numbers, because arrays you can't have partial ownership over an array. So, I believe this is this is the point where it fails due to the fact that we can't make this a mutable reference to the second element in the array. I believe this will not compile. Would you agree, Keith? I'm just going to wait a moment, unless you, do you have anything to say at this point? Are you following along? I could understand if not. I am struggling a bit. But it is already mutable. Point is mutable? Yes, point is mutable, but it no longer has ownership. The mutable reference? Yeah, I don't think it does change anything. If this was a tuple, it would. But since this is an array, I don't think that the mutable reference changes much. So y is a mutable reference to the second element in the array, meaning we cannot point y to a different thing. It will always point here. It cannot point to anything else. However, you are allowed to change what value 1 is. So if we didn't have this, the dereference of y plus equals 1 would be fine. You could change that. But since you however, since we're already changing ownership over, I believe this will fail. I believe I'm correct in that, but I guess we will see now. First one is correct. Second one is correct. String is free twice. Third one is correct. There's no undefined behavior. I almost got caught on that. Fourth one is incorrect. Here we go. I'd like to know why. Fifth one is incorrect. The program does compile. Let's see the correct answers. Right, so the first issue here, none of them will compile. None of them will work. None of them will work. Okay, yeah, the error is inside of the function. No, it can't be inside of the function. It tells us explicitly that it's not inside the function. Let's read the context. The statement let mute name equal dereference name makes name take ownership of the input string. However, the caller also still retains ownership of the string. Therefore, after award_phd finishes, the string is deallocated. Therefore, okay, the issue here, I see. I wouldn't have caught that, actually. I don't think I'll ever catch that. Right, so when we pass something into here, and it runs it, at the end of it, it's just going to delete name. Name is gone. It's gone entirely, because name has ownership over it. Once the function ends, everything which is owned by this function is deleted. It's yeeted out of there. It's destroyed. Well, that's not true. It's not destroyed. It's no longer owned. It's de-owned, deallocated. It's freed. So, name in this function is also destroyed after award_phd. So any use of it is not allowed. But why is this one incorrect? Therefore, every program above has undefined behavior because name will eventually be deallocated a second time. It does not matter whether name or a reference to name is read after calling award_phd. Okay, yeah, that's fair. I'm glad that they're beating our heads over this. I will never remember that at the end it will drop it twice. It'll drop everything within it. Alright, so confirm. At the end there's a hidden invisible reference to drop, and it will drop every single thing which the function owns. Anything which has ownership within this function. Secondarily, at the end of the original functions, there will be a reference to drop, which will drop everything within this. So if we pass ownership to award_phd, so I guess it serves as a bit of a garbage collector, since it frees mem for you. Kinda, yeah. Kinda. I mean, a garbage collector would see that it is still being used and not free it. But essentially, yes, this is a part of garbage collection. This is just, what is the word? This is garbage collection done automatically for you in a non-garbage collected language. You're correct, though. This is quite a lot like a garbage collector. A bit of a garbage collector, yeah. Thank you for that. That is correct. Thank you, Geek. Right. I answered that this does not compile. This program will compile, and the reference will be 0 and 2. X plus equals 1. Okay? Oh, because this copies. Okay, so this copies. This copies 0 over 2x, and then adds 1 to 0, which will be 1. But, point, the first piece of point, will not be changed. So this is not a reference to the first one. This is simply passing back by value because it has the copy trait. I see. So x is fine. X is perfectly fine. I guess, yeah. So what changes, as you were saying beforehand, what changes here with the reference to the mutable reference to point 1, it allows you to change this section whenever you change y. Okay, so, but here we are simply passing by value. Point 0 returns 0, the value, not a reference to 0. But if this was a string, it would pass back the word 0 or hello world or whatever it was. In this section, so this passes x the value of 0, creating a new point of memory where x is a mutable I32 called 0. Y, however, is just a reference to 1. That simply says, hey, I am 1. This is the second value within point. So, when we change x, that's fine because it's just nothing. When we change y, that's fine because it's a reference to the second piece of point. When we print it out, we have point 0, which is still 0, it has not been changed, and point 1, which is now 2, because we have changed it. That makes sense. This program does compile as the binding of x copies point 0, allowing y to mutably borrow point 1. The mutation x plus equals 1 does not affect point, while the mutation of dereference y plus equal 1 does. So the final result is 0 space 2. Alright, that does make sense to me. I understand why I didn't get that. I can see that I am not... the information is not connecting completely. It's not locking in my head. I can understand what it is saying, but I am not internalizing it. That seems to be an issue. I'm glad that it continuously bashes this into my brain, but I'm not going to fully understand until I start coding. When fixing an ownership error, you should ask yourself, is my program actually unsafe? If yes, you need to understand the root cause of the unsafety. If no, then you need to understand the limitations of the borrow checker and how to work around them. Okay, stop that. I guess I didn't turn it off. You guys just saw my D&D game. You guys can't know. You guys can't know. I am a nerd. The guy learning Rust is in fact a nerd. You guys aren't allowed to know that. Wow, how dare you. Right, okay. We are finished with that section of 4, Understanding Ownership. It only took an hour to finish the last half of that section. We are going into day 4 of learning the 4th section? I don't know, honestly. The slice type. Slices let you reference a contiguous sequence of elements in a collection rather than the whole collection. A slice is a kind of reference, so it is a non-owning pointer. To motivate, that is the word, to motivate why slices are useful. What in the world does that mean? To motivate why slices are useful? Whatever, who cares? Let's work through a very small programming problem. Write a function that takes a string of words separated by spaces and returns the first word it finds in that string. If the function doesn't return a space in the string, the whole string must be one word. So, the entire string should be returned. Without slices, we might write the signature of the function like this. Function, first underscore word, is, takes in s, which is a reference to a string, and returns a question mark. Who knows what it returns? The first underscore word function has a reference string as a parameter. We don't want ownership of the string, so this is fine. But what should we return? We don't really have a way to talk about part of a string. However, we could return the index of the end of the word, indicated by a space. Let's try that, as shown in listing 4.7. This is listing 4.7. The function will be taking in a string, which is a reference to a string, returning u size, which is just going to be the index. Let bytes equal s dot as underscore bytes. Oh, thank you for that. For index and reference item in bytes.iter.enumerate. Okay. So bytes will be an array or a struct or some different collection of each of the string's letters. Okay, that's fine. Reference item will be a reference to the as byte char, the character for each letter in the string. And if item equals the binary of a space, we will return the iterator. If it fails completely, we will simply return s.length. There's no if statement showing that, but if we return here, we have found something that equals the bytes of space, the char of space, as a number, and we will return out of the function I. However, if it all goes pi without finding a single reference to a space within within the original string, we will simply return s.length. Because we need to go through the string element by element and check whether a value is a space, we'll convert our string to an array of bytes by using the asBytes method. Let bytes equal s.asBytes. Next, we create an iterator over the array of bytes using the iter method. For I, comma, reference to an item, in bytes.iter.enumerate, creates an iterator, and then creates an enumerator over an iter. I don't know, man. We'll discuss iterators more in chapter 13. It doesn't matter for now. For now, know that iter is a method that returns each element in a collection, and that enumerate wraps the results of iter and returns each element as part of a tuple instead. Makes sense. The first element of the tuple returned from enumerate is the index. The second element is a reference to the element. That is a bit more convenient than calculating the index ourselves. Makes sense. Because the enumerate method returns a tuple, we can use patterns to destruct that tuple. We'll be discussing patterns more in chapter 6. In the for loop, we specify a pattern that has I, the index, in the tuple, and item, the single byte in the tuple. Because we get a reference element from .iter.enumerate, we use reference in the pattern. Inside the for loop, we search for the byte that represents the space by using the byte literal syntax. If we find a space, we return the position. Otherwise, we return the length of the string by using s.length. We've discussed this. That is what it is doing. We now have a way to find out the index of the end of the first word in the string. But there's a problem. We're returning a u size on its own, but it's only a meaningful number in context of reference string. In other words, because it's a separate value from the string, there's no guarantee that it will be valid in the future. You could destroy the string, you could change the string, stuff like that. Consider the program in listing 4.8 that uses first_word function in listing 4.7. We have a function, first word. We have that function that's been used. Main. Let mutable s equal string from hello world. S has read, write, and ownership. Let word equal first_word s. This is location 1. S dot clear. We clear out s. Alright, so at location 1 we have s, which has the location, which points to hello world in the heap, the string. In location 1 we also have word, which will equal 5. This index. At location 2, when we clear s, s points to nothing, an empty heap address. S points to a string which is empty. There's still something there. There's the string which is empty. There's still an array in the heap, but the array holds nothing. Storing the result from calling the first_word function and then changing the string contents, that is 4-8. This program compiles without any errors, as s retains write permissions after calling first_word, because word isn't connected to the state of s at all. Word still contains the value 5. We could use that value 5, the variable s, to try to extract the first word out. This would be a bug, because the contents of s have changed since we saved 5 in word. Having to worry about the index in word getting out of sync with the data in s is tedious and error-prone. Managing these indices is even more brittle if we write a second_word function. Its signature would have to look like this. We would have to have the beginning of the word and the end of the word. Now we're tracking the starting and ending index, and we have even more values that were calculated from data in a particular state, but aren't tied to that state at all. We have 3 unrelated variables floating around that need to be kept in sync. Luckily, Rust has a solution for this problem: string slices. A string slice is a reference to part of a string, and it looks like this. Let s string come from hello world. Let hello is a reference to the string, reference string 0.5. Let world reference string. Let hello, which is the type reference string, equal reference to the string between 0 and 5. Okay, so that's the first 5 letters in hello world, whereas world will equal a reference to the string reference s 6 to 11. So be the world word. Wow, great explanation of the code, my dude. Let s2 equal reference string reference s, the original string. This is fine. Alright, so s will equal hello world, hello will equal just hello, world will equal just world, and s2 will be referencing s, meaning we need to double dereference in order to get hello world. Rather than a reference to the entire string like s2, hello is a reference to a portion of the string, specified in the extra 0.5 bit. This is a range. We create slices using a range within brackets by specifying inside the bracket the starting index to the ending index, where starting index is the first position in the slice and ending index is one more than the last position in the slice. How does ownership work with this? Slices are special kinds of references because they are fat pointers, or pointers with metadata. Here is the metadata. Here, the metadata is the length of the slice. We can see this metadata by changing our visualization to peek into the internals of Rust's data structure. I rarely do. Right. So we have main, which has s, which is a string, which is a vector with a vector inside of it and the value of length. Vector has a buffer, which holds another raw vector with the cap, the max size of the raw vector, and a pointer, which is a pointer to a unique, which is pointing to a pointer to non-null, and a pointer to hello world. You guys understand that? You guys get that? Okay. That's just how a string works in this language, which is how string works. Not exactly how string works in all languages. Usually it's just a pointer to the first member of an array, but hey. Observe that the variables hello and world have both a pointer and a length field, which together define the underlying region of a string. On the heap, hello has a pointer to hello. That's really nice, thank you. Okay, if we scroll to the right, it won't act. I don't understand that shit. Kinda 1%. You understand? Fantastic, better than I do. I don't know what a unique is, don't know what a raw vec is, don't know what a buffer is. Well, I kind of understand what a unique is, but you know, hey, what are we going to do about that? Right, so hello is just a pointer, the entirety of hello, the length of 5. World is a pointer, the entirety of world, the length of 5. S2 points to the original S. You can also see here what a string actually looks like. A string is a vector of bytes, vec u8, which contains a length and a buffer, buff, that is a pointer, and a capacity, cap. Okay. Yep, S is a string, which is a vector holding a vector and length. Okay, whatever. We can kind of understand that. A string is simply a vector of bytes, vector u8, which contains a length, len, and a buffer, buff, that is a pointer, and a capacity of count. Because a string is just a bunch of letters, and a bunch of letters are just a bunch of numbers. A char is just a number which references the letter. For example, and this isn't the exact values, A would equal 0, B would equal 1, so on and so forth. And we're outputting it, we simply get the letter which is referenced by the value. That's how strings work in all languages, because computers can only understand ones and zeros. They can only understand numbers, so hey. Because slices are references, they also change the permission on reference data. For example, observe below that when hello is created as a slice of S, then S loses write and own permissions. Makes sense? Because if we can change S, then hello is also changed. If we take out the E, that's HLLO space, and now hello doesn't just contain hello, it also contains that space. If we delete it all, this is pointing to empty space, so it makes sense that S would lose write and ownership permissions the second that hello is created. However, hello has write and ownership permissions. If we allow this to be mutable, I would assume that we have that hello would also have writable permissions, and we could change those as long as we keep within the 0 to 5 structure. This is an assumption, perhaps it is incorrect. When we utilize it, we have S regaining read, write, and ownership, and hello losing read and ownership, because it is no longer used after this point. It is essentially dead at this point, and immutable S regains what it had before. And we are allowed to push onto it world. However, after it is used, it is destroyed at the end. We drop S. S is dropped at the end of this function, and it loses all ownership privileges. With Rust ... range syntax, if you want to start at index 0, you can drop the value before the two periods. In other words, these are equal. 0.2 is equal to ... 2. So 0 to 2 is the same as until 2. And by the same token, if your slices By the same token, if your slice includes the last byte of the string, you can drop the trailing number. That means these are equal. S equals a string from hello. Length equals the length of S, which would be 5. Slice equals the reference to S until the length, or S until the end of the string. You can also drop both values to make the slice of the entire string. So these are equal. String from hello, let length equal S dot length, slice S equals 0 to length, or slice equals reference S dot, the entirety of S. Why would you want that? Why would you want a slice, which is just the entirety of the string? Maybe there's things you can do with a slice that you can't do with other things. I don't know. Who cares? String slice range indices must occur at valid UTF-8 character boundaries. If you attempt to create a string slice in the middle of a multi-byte character, your program will exit with an error. For the purposes of introducing string slices, we are assuming ASCII only in this section. I was wondering about that. What about Windows, which uses UTF-16 by default? From our more thorough discussion of UTF-8 handling is in the Storing UTF-8 Encoded Text with Strings section of Chapter 8. We'll learn about that in about 3 months. Hell yeah. With all this information in mind, let's rewrite first_word to return a slice. The type that signifies string slice is written as reference str. Okay. I hate how nearly every language has strings and strs. I can never remember what they are, to be clear. Maybe I'll remember it in Rust because it's a slice. First word, S, reference string, returns a reference to a string slice. Let bytes equal S as bytes for every character. If it is space, return a slice from 0 to the index, the point where that space exists. If not, we want to return the entirety of S as a slice. Here's why. Because we need to return something. We need to return a slice. We need to return a slice if this works normally, but we may need to return the entirety of the string in the end of this. That makes sense. Okay, but also we could just leave out that 0 if we so wished, I believe. We get the index, the end of the word, in the same way we did in listing for 7, by looking for the first occurrence of a space. When we find a space, we return a string slice using the start of the string and the index of the space as the starting and ending indices. Okay. Now we call first_word. We get back a single value that is tied to the underlying data. The value is made up of a reference to the starting point of the slice and the number of elements in the slice. Returning a slice would also work for a second_word function. Now we have a straightforward API that's much harder to mess up because the compiler will ensure the references to the string remain valid. Remember the bug in the program from 4.8 when we got to the index? When we got the index to the end of the first word and cleared the string so our index was invalid, that code was logically incorrect but didn't show any immediate errors. The problems would show up later if we kept trying to use the first word index with an empty string. Slices make this bug impossible and let us know we have a problem with our code much sooner. Right? Showing here we have the string S for hello world, letting word equal the first word, which loses S is right and ownership privileges. So when we attempt to use it and mutate it, it fails. You can see that calling first_word now removes the write permissions from S, which prevents us from calling s.clear. Here's the compile error. Right, I'm kind of curious about what this is. Compiling ownerships. Error. Cannot borrow S as mutable because it is also borrowed as immutable. Immutable borrowing occurs here, right, when we pass it into first word. Mutable borrow occurs here when we try and clear it. And then a use is here. Immutable borrow later used here. Recall from the borrowing rules that if we have an immutable reference to something, we cannot also take a mutable reference, because clear needs to truncate the string. It needs to get a mutable reference. The print line, after the call to clear, uses the reference in word, so the immutable reference must still be active at that point. Rust disallows an immutable reference in clear and the immutable reference in word from existing at the same time, and compilation fails. Not only has Rust made our API easier to use, but it has also eliminated an entire class of errors at compile time. Okay, that's good. String literals are slices. Recall that we talked about string literals being stored inside the binary. Now that we know about slices, we can properly understand string literals. So when we have S equal a literal hello world, the type of S here is a reference to a string or a slice of a string. It is a slice pointing to a specific point of the binary. It is also why string literals are immutable. String slice is an immutable reference. Okay. Yeah, it is an immutable reference. Okay, that's good to know. Knowing that you can take slices of literals and string values leads us to one more improvement of first underscore word, and that's its signature, which is currently S of a reference to a string, returning a reference to an str or a string slice. A more experienced Rustacean would write the signature shown in listing 4-9 instead, because it allows us to use the same function on both reference string values and reference str values. Function, first words, S, which is a string slice, returning string slice. So, okay. Okay, so would we have to turn this into a string slice, or would it automatically typecast? If we pass a string slice, we can pass that directly. If we have a string slice, we can pass that directly. If we have a string, we can pass a slice of the string or a reference to the string. This flexibility takes advantage of deref coercion, a feature that we will cover in implicit deref coercion with functions and methods. So yeah, it'll automatically convert a reference to a string to a slice. I think that'll be discussed in chapter 15. Defining a function to take a string slice instead of a reference to a string makes our API more general and useful without losing any functionality. Right, so we have myString equals hello world, word equals first word, myString 0-6. A reference to myString, sliced 0-6. That word equals first world, word. Let word equal first word, myString, which is a reference to myString, sliced to be the entire string. First word works on slices of strings, whether partial or whole. Correct. First word also works on references to strings, which are equivalent to whole slices of string. So we can just pass in a reference to my string. We don't have to cast it. We don't have to change it in any way, shape, and or form. We can just pass it in if we so wish. Let my string letter equal hello world. We can pass in a slice of hello world, the literal, or the entirety of it, because both are slices. So we can create a slice of this literal, which is already a slice, and then pass that in. However, since it's already a slice, we can also just pass in the entire thing. Good to hear. We don't even need it to be a reference to my string literal. A, because it's immutable, what are you even going to do with a reference? And B, because it's just a literal. Right, other slices. String slices, as you can imagine, are specific to strings. There's a more general slice type too. Consider this array. A equals 1, 2, 3, 4, 5. Just as we might want to refer to a part of a string, we might want to refer to part of an array. We do so like this. A equals 1, 2, 3, 4, 5. Let slice equal the reference of A, 1 to 3. Assert equal slice, the entirety of this, and 2, 3. Right, yeah? So slice is an array, is a slice of this array, 2 and 3. And this is a reference to an array, 2 and 3. The slice has type, reference I32. It works the same way as string slices do, by storing a reference to the first element and a length. You can use this kind of slice for all sorts of other collections. We'll discuss these collections in detail in Chapter 8 when we talk about vectors. Let's do the quiz. Consider the variables S2 and S3 in the following program. These two variables will be located in memory within the stack frame for main. Each variable has a sign in memory on the stack, not including the size of pointed data. Which statement is true about the sizes of S2 and S3? Right. S3 has the same number of bytes as S2. Alright, let's look at this. We have hello. S equals a string called hello. Let S2 equal a reference to the string. Let S2 of the type of reference to a string equal a reference to S. Let S3 equal a reference to a str or a string slice equal to a reference to S, which is sliced into the entirety of itself. That's hello. Response. S has the same number of bytes as S2. S has more bytes than S2. S has fewer bytes than S2. It should have the same amount of bytes because it's just the entirety of it. I believe so, though I believe that str would actually have more bytes because it's more information. But let's respond with the first, because I believe that's what it's trying to state. Determine whether the program will pass the compiler. If it passes, write down the expected output of the program as if it were executed. Let mutable s equal string from hello. For every item in S as bytes, so H, E, L, L, and O, written as numbers, we want to create an iterable, and we want a reference item to be the output for the for loop. If item is equal to the byte of L, so if item is L, if the letter is L, we want to push to the mutable S, the string world. Okay, and then we want to print S. So we'll go through H. Is that L? No. E, is that L? No. L, is that L? Yes. Yes, that is L. Thus we add space world. Is that L? Is this L? Add world. Is this O? Add it. This could cause don't do this. This could cause an infinite loop. Is O L? No. Stop. Well, no, actually, it won't stop. Will it stop? Okay, so my issue here is that we are adding to the thing that we are iterating over. S.asBytes.iter, I believe, will that take ownership over S? Can we mutate S at this point? Because we are currently... No, we're just returning an iterable, so... a reference, though, so... let's just say this does compile. My issue here is that we have s.asBytes.iterable, which should pass back an iterable of references to item, which will be H, E, L, L, and O. Does item reference the H here, or is a new hello created which item is referencing. If so, then this is fine. If it isn't, and in fact item is pointing directly to the H, that will not be fine, I don't believe, because we are then mutating here. I think it's fine though, because I don't think that's what's happening here. We then push in world twice. So if this does compile, we will put hello, hello, world, world. Because there are two L's in hello, and we are adding world once for every time that there is an L in S. Okay, let's submit. First one was incorrect. S has the same... Right, I believe that it has more, correct? This is more information. This does not compile. Okay, let's see the correct answers. I am entirely incorrect here. S3 has more bytes. Yes, I was correct in my assumption. Alright. So what's different here is that we have more information here. Sure, S is a slice of hello, but we also, on top of that, require the knowledge of how long S is. We need the length, which is 5. So not only do we have a reference to hello, we also have the length of the a slice of hello. We also have the length of the slice. So there are more bytes in S3, is my assumption. The type, reference string, is a normal reference consisting of a single pointer. I am an idiot. Okay, so 8 bytes on a 64-bit architecture. A string is a special slice reference, which consists of a pointer and a length, so 16 bytes. Therefore, S3 of type string slice uses more memory than S2 of type string. I didn't think that's what he was talking about, but yes. You can verify this for yourself by using standard mem size of. So, yep. So standard mem size of will just give you the size of a string, or a string slice, or anything you put in here, any type. That makes sense. So to confirm, S3 not only has a reference to hello, but also the length. The size. The length of the slice. However, S2 is just a reference to S, meaning it will be just the pointer. It will be just one pointer. Also note that Rust will implicitly convert string references to either reference string or reference string slice based on the context of the reference. So the expression reference S produces two different values based on the expected type of reference S. Question 2, this will not compile because s.as_bytes produces an immutable reference to S. It is illegal to mutate S. So again, I was correct on this, but I said it would compile anyway. So s.asbytes.iter does in fact create a reference to S. So the reference to item is directly pointing to the H, the E, the L, and the O, instead of creating a new hello and then iterating over each different section of it. Makes sense. So this can't compile because we are trying to mutate something we do not have ownership over. Okay. Is that understandable? I'm sorry, Keith. I'm not the best at explaining this stuff without a person who I can talk directly to. It is reasonable that you can't understand all of this. Okay. Right, so we are at the summary. Slices are a special kind of reference that refer to subranges of a sequence, like a string or a vector. At runtime, a slice is represented as a fat pointer, which contains a pointer to the beginning of the range and a length of the range. One advantage of slices over index-based ranges is that the slice cannot be invalidated when it is used. Alright, that is great. However, I am thinking that this is a great place to... No, it isn't actually. We have... No. We have the recap, which we will do next week. It is currently an hour and 49 in. So I believe this is where I will end. Thank you so much for being here, Keith. I wish there were others here, but sadly they did message me saying that they couldn't be. Still though, thank you for being here, Keith. I do enjoy your company. Thank you for listening to me ramble. Keith, if you want to talk in a live chat, just me and you, no stream, nothing, about what we've talked about, to try and A, as a bit of a recap for myself, to help me understand a bit better, or B, to help you understand, I would love to set that up. You can message me on Lemmy if you're interested in that, and we can set up a time for us to have a Skype call, a Discord call, or something else, just to talk to each other about this specific thing. Is that something you'd be okay with? That's something you'd be interested in? Good work. Fantastic. Simply message me and we can find a time that works for both of us. Of course, anybody currently listening to this who also wants that, I'd love to talk to you. You can also find me on Universidon. Thanks, Keith. I'll message you on Mastodon. I'll admit, Mastodon is a bit better at messaging. I do prefer that over Lemmy, and I would like to use Mastodon a bit more. Okay, and with that, I think that is the end of our conversation. Once more, I really do appreciate you being here. I'll see you next week, but hopefully before then. I'm going to click the stop stream now.